In this module, I'm going to provide you an introduction to the paper Regression 3. Now, you have already studied two papers on regression as part of the MSc syllabus. In the first paper, we provided you an exposure to ANOVA models, ANCOVA models, and regression models, and we saw that they're all special cases of something called the linear model. We introduce you to the Gauss-Markov setup, which is a very comprehensive setup and can be applied to a wide range of applications. In the second paper on regression, we saw that the Gauss-Markov setup need not necessarily hold always, and we provided you with tools to use when the Gauss-Markov setup does not hold. So taken together, the first two papers on regression provide quite comprehensive coverage of a wide range of models and applications. The question then arises as to why we need yet another paper on regression. That is what I'm going to provide you an overview of with the help of 4 examples in this introductory module. In this paper, we will look at regression models for the case where the outcome is discrete. So to look at some specific examples, we might look at cases where the outcome is binary, for example, whether or not someone has lung cancer, yes, no. We might look at the proportion or percentage of people who have lung cancer, the percentage of literates, and so on. We might also look at a particular kind of count, like the number of accidents happening in a particular area in a particular time, the mortality rate, and so on. Now we will look at the theoretical framework for this kind of analysis in subsequent modules and indeed for much of this paper. In this module, I'm going to look at 4 motivating examples and try and motivate the contents of this paper. When we look at the theoretical framework, we will see that this leads to a particular class of models called the generalized linear model, of which the linear model, which you have studied in Regression 1 and Regression 2, will emerge as a special case. But more on this later. For now, let us look at 4 motivating examples. Our first example is from a clinical trial. For those of you who might not be familiar with a clinical trial, this is a randomized, placebo-controlled, double-blinded study design. It is randomized because we randomly allocate 2 or more treatments to 2 or more study groups. It is placebo-controlled in the sense that while we give the treatment under study to one group, we cannot really not give anything to the other group or not have the other group at all. To reduce scientific bias, we give them something called a placebo, which is in fact a drug which does not have any active ingredients. It is double-blinded in the sense that neither the recipient of the treatment nor the person allocating the treatment is aware of which particular regimen a particular subject may have received. If you are interested to know more about clinical trials, you will get more exposure on this in the modules on biostatistics. For now, let us look at a clinical trial of aspirin use and myocardial infarction. So my question of interest is, of course, does regular intake of aspirin reduce mortality from cardiovascular disease? So here is the data. This is data which you might be familiar with from your undergraduate classes. It is the usual 2x2 table where along the rows we have looked at whether or not someone has been given placebo or aspirin, and along the columns we have looked at whether or not they suffer from myocardial infarction. So for example, 189 people on placebo experienced myocardial infarction. The source of this data is from a study of the ongoing Physicians' Health Study, which was published in the New England Journal of Medicine. So to look further at the data, of the 11034 physicians who were given placebo, a proportion of 0.0171 suffered from MI, while of the 11037 physicians taking aspirin, a proportion of 0.0094 suffered from MI. We can calculate the difference, which in fact is technically called the risk difference, as 0.0077. We could also choose to look at the ratio of the proportions. Now technically this is called the sample relative risk, and we can calculate it for this example as 1.82. We can also calculate something called the odds ratio, but more on the odds in our next example. Now the analysis so far has not really required new methods, although we have introduced two new terms called the risk difference and the risk ratio. Now note that this example could just as easily have arisen from an observational data setting rather than a clinical trial. Now, in a clinical trial, we do not necessarily collect information on covariates because many statisticians believe that when we randomly allocate the placebo and the drug, the distribution of the covariates will be more or less identical in the two groups. However, not all statisticians believe in this, and in that case, it is necessary to account for all these additional covariates. We have thus a typical regression setting, with the exception that my outcome is now whether or not someone has MI, which is considered binary. We will look again in a following example on why the usual linear model is not applicable to the case where we have a binary outcome. Let us move on to example 2. Now we can see here a similar 2 by 2 table in example 2, where along the rows we have looked at whether or not a person is a smoker, and along the columns we have looked at whether or not the person has MI and something which has been referred to as a control. Now, although this table is similar in appearance to the table which arose from the clinical trial, in practice it is in fact very different. Now, suppose you have been asked to perform this experiment and collect the data. There are many ways in which you could do this. So one would be you could look at a random sample of, say, N patients and ask each of them whether or not they smoke and whether or not they have MI. However, as MI is a rare condition, unless you collected a very huge sample of data, you would not really get very many cases. So, the kind of study which has been used to collect the data is what has been written in the first line on this slide, which is a case control study. Now, common sense tells us that it would be easier to collect the data if we went somewhere, maybe to a hospital, a cardiac hospital, where we were likely to get cases of MI. So that is exactly what we have done here. We have looked at cases who have been diagnosed with MI and a group of controls, which are people who have not experienced MI. For each group, we have looked at whether or not the person ever was a smoker or not. Now, there is another subtle point here, which is that along the columns, I have classified subjects as having experienced MI and not having experienced MI. Now, having experienced MI is relatively easy to identify from physician records, but not having experienced MI is not really a very descriptive idea. So, if they have not experienced MI, does it mean that they are perfectly well? In which case, are they comparable to the people I'm looking at as cases? Does it mean that they have experienced some other illness, which is not MI? And what happens if smoking is also a risk factor for this example? So, this in fact relates to something called choice of the control group, and again more on this in the modules on biostatistics. For now, we take home the message that when we see a 2 by 2 table, there are many ways in which we could have collected the data, and here we have introduced something called a case control study. However, there is an extra problem here. Let us define this in terms of random variables x and y. Now, whenever we have a regression setting, x and y are not really exchangeable, but the expectation is that we can use x to predict y. If that is our focus, then in this example, it makes more sense to consider smoking status as x and MI as y. So MI is the outcome and smoking status is explanatory, and we wish to predict the occurrence of MI using information on smoking status. That is, we wish to predict y given information on x. However, if we look back to how we have collected the data, we have done so using a retrospective design. That is, we have collected data from x given y. So the marginal distribution of MI is fixed by design. What this means is that we have fixed how many cases we want to sample and how many controls we want to sample. And in this case, we have looked at the distribution of x. This is something called a retrospective design and needs extra methods for analysis. The reason why we need extra methods for analysis is that the risk difference or risk ratio, which we looked at in the first example, cannot be calculated here for the same reason listed on the earlier slide, which is that the marginal distribution of MI has been fixed by design. However, it turns out that even though the risk difference or the risk ratio cannot be measured, the odds ratio can in fact be measured. So the odds ratio, which is given here, turns out to be 3.82, which says that smoking is indeed a risk factor for MI. It turns out that for very rare disease, the risk difference, the risk ratio and the odds ratio are relatively close to each other, and the odds can thus indirectly be used to approximate risk. So these are some complications when we have data from a case control study. Let us move on to a different example, which illustrates a slightly more complex collection of data. So in technical terms, this is a 2 by 2 by 2 table. The three factors which we look at here are whether or not the death penalty has been awarded in a particular murder, whether or not the victim of that murder was white or whether he was black, and whether or not the accused or the defendant was white or whether he was black. The source of this data is the Florida Law Review, and this was data collected on a sequence of murders which occurred in Florida. This data set is well studied in the source which has been quoted here and also in the book on Regression. So again, to repeat, this is data from a 2 by 2 by 2 contingency table where we are looking at three variables. Y, which is the death penalty, and we measure this as yes/no. X, which is the race of the defendant, which we measure as white or black. And Z, which is the race of the victim, which is also white or black. So we have a 2 by 2 by 2 table made up of three binary variables. Now let us zoom a little bit more into the data. In the first example, I have aggregated over the victim's race. So when I do that, it turns out that 11% of those cases in which the defendant was white were awarded the death penalty. 7.9 cases were awarded the death penalty when the defendant was black. So in this case, we can say that whites were more likely to be awarded the death penalty. Let us now look at the two partial tables in the case where the victim was black and the case where the victim was white. Now we see something odd in this data, which is that when the victim was black, it seems that black defendants were more likely to get the death penalty. Similarly, when the victim was white, again, black defendants were more likely to be awarded the death penalty. Yet we see that when we collapse the data and add the two tables, it turns out that white defendants were more likely to be awarded the death penalty. So this is a classic paradox when we analyzed discrete outcomes and is referred to as Simpsons Paradox. Technically, the reason is that conditional and marginal associations indicate different conclusions. We shall look at this example in greater detail in a subsequent module. My next motivating example is the Challenger disaster. Now, if you do not remember what happened to the Challenger space shuttle, let us look at this video. So we just saw a video in which the Challenger space shuttle veered off course, exploded, and the debris crashed into the Atlantic Ocean. So the Challenger space shuttle happened in 1986. It killed all the crew on board, and it led to a hiatus in NASA's space program for quite a few years. Later, suspicion for the crash was fixed on the failure of a piece of equipment called the O-ring. Now, in each of the two boosters on the rocket, there are 3 O-rings, leading to a total of 6 O-rings. It turns out that there was controversy as to whether or not these O-rings had been adequately tested, and there was some belief that at low temperatures, the O-rings could fail. At the time of launch, the temperature was 31 degrees Fahrenheit, and the question which arises in this case is whether or not we could have predicted the failure of the O-ring at 31 degrees Fahrenheit. Now here I'm showing you a plot taken from a dataset called O-rings from R, where we have looked at 23 satellite launches, and in each case whether or not the O-rings failed and the corresponding temperature. Now, if I do not know any other methods and naively apply the linear model to this data, this is the result that I get. And the plot here does not look quite right, in the sense that if I could continue to extrapolate this curve to the left, at some point I would go beyond 1. But we know that probability is necessarily between 0 and 1, and thus it is troubling here that fitting the linear model leads to predicted probabilities which do not necessarily lie in the range 0 or 1. Now, a quick overview of what we will do for most of this paper. I have fixed this by introducing a link function called g, where rather than saying that probability is a linear function of temperature, we say that some function of probability is a linear function of temperature. This function is called the link function. Of course, choice of the link function is not necessarily straightforward, and 2 choices are listed here called the logit and the probit link. Now what these are and how we choose them and how they are fitted are details which we will explore in the remainder of this paper. Now here, however, are the results from fitting logit and probit links to the data, and we see an example which is more satisfactory in the sense that the predictions plateau off either to 1 or to 0 at the two extremes. And we can also see that the results suggest that the probability of failure at 31 degrees Fahrenheit was quite high, which says that yes, indeed, we could have predicted the failure of the Challenger space shuttle. To summarize then, this module provides you an introduction to the syllabus which we will cover in subsequent modules in Regression 3. We have looked at 4 examples. The first was an application from clinical trials where the 2x2 table per se does not need you to use regression techniques, but in any situation where we collect an additional set of covariates, we will need to build regression models for the case where the outcome is a proportion. In the second example, we introduce something new, which is the concept of study design. Now, you have always assumed that random variables are identically distributed and the sample that you are looking at is a random sample. We saw here that the study design which you use has a bearing on the analysis which you can use, and we introduced the idea of a case control design. The third example provides us an introduction to an interesting concept which is called Simpsons Paradox. And in the fourth, we saw that when we want to predict something which is a proportion or a percentage, we cannot really fall back on the methods which we have learned in Regression 1 and Regression 2, and there is a need to introduce new methodology. We will take up each of these examples and study remedies and tools for each of them in subsequent modules.